Dr. Jeffrey Zurek isn't just a geophysicist and volcanologist. He's a scientific storyteller who can turn gravity, magma, and plate tectonics into edge-of-your-seat narratives. He's an award-winning podcaster and a guy who has spent years chasing data everywhere from Hawaiian lava fields to the Arctic wilderness. Raised in a tiny town in British Columbia, fell in love with dinosaurs, and somehow ended up mapping the hidden architecture of volcanoes using some of the most sensitive instruments on Earth. He's worked in places where you carry a shotgun for polar bears, measured gravity changes smaller than anything a human could ever feel, and he's helped unravel mysteries inside Mauna Loa that most people don't even know exist. But what makes him unique isn't just the science, it's the way he brings it to life. His podcast, Whimsical Wavelengths, just won a national award for making complex research accessible, human, and genuinely fun. Want to know why gravity might not be constant across cosmic time? Why insects used to be the size of house cats? Or how a landslide 100,000 years ago changed the plumbing of the world's largest volcano? Me too.
You know, the podcast is called 4Fs because there are 4Fs in my name. So like, I feel like it's good. The 6Fs. This is our first time to have another Jeff on, and 6Fs today. It's a good thing. So Jeff, the podcast always starts the same way, which is basically tell me where you're from, man.
Yeah, so I grew up in a tiny little town in Canada, British Columbia, specifically called Castlegar. I think it had about 7,000 people. I don't know what to say. It's a small town in Canada. You know, forestry is the main type of what most people do for a living, even still today, I would say. And yeah, it's where the confluence of the Columbia River meets the Kootenay River.
All right. So that's like as Canadian as it gets, because like if you're saying the main industry is forestry, aka lumberjacks, right?
Don't tell me I have to start singing "I'm a lumberjack and I'm okay."
Is that a thing? Is I'm a lumberjack and I'm okay? Is that a real song?
Well, I mean, it is a real song, but it was put out by the British Canadian group. Oh my gosh, why am I pulling a blank right now?
That's all right, because your lumberjack trivia is, you know, it's a little rusty. Maybe.
Monty Python.
Of course, Monty Python.
Yeah. Sorry, just pulled a blank for some reason. I really shouldn't have.
It's great. It's classic. So, sorry, what was the name of it again?
Castlegar.
Castlegar.
It's a funny little town, really, when you think about it, because, I mean, this is probably also the case in the States. As different groups of migrants come in over time, they settle in tight little areas.
Sure.
And so Castlegar was settled originally, I can't remember the exact date, but somewhere around 1900, might even been before, by Doukhobors fleeing Russia. And so they have a particular, you know, culture, and, you know, we had lots of borscht, for instance, even though that's not a very Canadian dish. That's what, you know, you grew up around. And yeah, it's just, it's an interesting place. And then you don't have to go very far and you go to Trail, and that's where a lot of Italians kind of settled. So it is, even though it's rural Canada, the roots are still quite multicultural.
Okay.
Even if you don't necessarily see it at the surface when you're driving through.
That's cool. I love little pockets like that. I mean, you wouldn't expect it when you show up in small town in the middle of the Western Canada to just be like, yeah, there's, you know, this great borscht around here. But you know, people show up, they settle into town, and I like that a lot. That's a cool piece of history there. How did you end up there? I mean, obviously you were born there, like you said, but I mean, how did
yeah. So this gets a little, I guess, into the weeds, but my grandfather on my dad's side was actually in Poland during the Second World War, and we could make a whole podcast on his life, that's for sure, because he was right of the age, I guess, 16-ish when Russia invaded Poland.
Oh, wow.
And then he started fighting the Russians, and then Germany invaded Poland. So he went from a Russian internment camp where he was captured, escaped, got put into a German internment camp, apparently escaped with some Russians, but was injured in the process. The story goes that the other 7 Russians died in the escape attempt, made it to the French underground, then all the way to Britain, joined the Polish brigade of the British Army, and then couldn't go back because Poland was behind the Iron Curtain. So, because he started the war fighting the Russians, he was scared to go back. So He came to Canada. And so when he came to Canada, he had some skills, but one of the things, I don't know, I think it's kind of random that he ended up in Castlegar and then got into the sawmill because that's where the jobs were.
Yeah. I mean, if you're like homeless all of a sudden without a country, then you're like, well, I'll work wherever, you know, all of a sudden anything seems like a great. And so the first place that is a job makes perfect sense. That's wild, dude. That's a pretty cool story.
And I don't know most of the details, right? Like there
Sure.
are some family members that do know more details than I do, but even that is like a skeleton is just wild to think about.
Seriously. As a skeleton, you mean like like kind of a skeleton in a closet, or just
No,
like
when you think of a movie or a script, it's a skeleton of a script. You still got to
okay.
add flesh to the bones.
Got it. Yeah, I see. Like the precursor to like the term flesh it out, right?
Yeah.
Got it.
Yeah.
Okay. Yeah, copy. Yes, that's a hell of a skeleton. No question about it. Okay, so thanks for going there. I think
Yeah, no
I don't know,
worries.
I find those things to be kind of interesting, or really interesting. All right, so you end up in Castlegar, and you're not end up. You're born in Castlegar, and then how, with the community being what it's being, like, how did you end up finding your way into science?
I was born weird. No, but like any kid, I fell in love with dinosaurs to begin with, right? And was kind of like, I don't know if fixated the right word, but I was like always in the dirt trying to find rocks and do these sorts of things. And so my mother eventually took me to the Royal Trail Museum, which is in Drumheller, Alberta. It's like
Okay.
one of the best dinosaur museums there is in the world, bar none. It's at least top 3 anyway, or maybe top 4, something like that. It's crazy. It's awesome. If you get the chance, you got to go. But part of that, being young, I learned how they took bones out of the ground and how they separated the fossil from the rock. It's a lot of painstaking work. Holy smokes. And as like a 5-year-old kid, I was like, I can't sit still for more than 30 seconds. I ain't doing this. And so from there, it was just kind of like, okay, well, I need something a bit more dynamic to look at. What about volcanoes? They go boom. That could be awesome. And then it just kind of stuck.
That's cool. The volcanoes, you don't have to take them out of the ground, because they come out for you, if you're lucky, right? They remove them, they do all the hard work. So all right, so look, you're not the first kid that gets into dinosaurs, right? I mean, I feel like lots of kids get into dinosaurs, but you didn't stop. You were like, I'm into dinosaurs, and then you started. You just kept going with science, and I mean, like, basically as far as you can get, right? I mean, were there any steps in between? Hey, I kind of like this as a kid, and then I like volcanoes. To, I don't know, to getting where you are now, or did it just kind of, I like dinosaurs first, and then now I like volcanoes, and then you just kind of follow the trail, and then you're right here, you're a PhD all of a sudden.
Well, I mean, like with every story, there's trials and tribulations as you move through life. And so it's easy to say it was pretty much a straight shot,
Yeah,
because it kind of was. I got to high school and I was like, okay, what courses do I need to study volcanoes? How
really.
am I going to do that? And so at some point I realized, well, I can't spell to save my life. And so biology means that's right out, because the biology teachers in high school required spelling or you lose half the marks. And I'm like, I'm not going to start with 50% of my grade gone. So, okay, well, how do I do this? Because that means geochemistry's out, straight geology's out. What about geophysics? And so that was the path I took to study volcanoes, was because I can't spell.
Makes sense. I like it. I really like the just like the really practical approach here. Like, okay, well, how am I going to do this? I know what I want to go into. I know my strengths and weaknesses. Let's get after it. So you mentioned a couple of terms just now, like you're comparing biology to something else, and to geophysics. Like I know the word. I know geology, study of. I think I'm gonna out myself maybe here right now, but geology, I think, is the study of rocks. But I don't know what the difference between geology and geophysics is, or any of the other ones. Would you mind helping me out with that?
Sure. Maybe.
However you want to explain it. I trust you.
Yeah. So it's like saying for anything, like there's a biologist, there's a chemist, there's a geologist, there's a physicist.
Okay.
So those are kind of like the main branches. And then within those branches, we have a lot of subdisciplines. So when we think of physics, we have astrophysics, particle physics. When we have geology, we can combine geology and chemistry and call it geochemistry, combine geology and physics, and we call it geophysics. So in this case, because I'm a geophysicist, what I'm doing is that I'm taking physics and essentially studying how the physics of the earth, right? I'm looking at how things like physical properties and physics really interacts with earth systems.
Okay. And when you say earth, earth systems, what are those?
It could be anything that we deal with on a day-to-day life. We walk outside, there's the atmosphere.
Okay. Yeah. Okay.
you feel an earthquake. Again, we're talking about the physics. If we start using,
all right,
compass to navigate, the compass is directed from the Earth's magnetic field, and that changes over time. Not to mention, if you measure the Earth's magnetic field, it's also affected by things underneath your feet. So if you have a big body of iron ore beneath your feet, you can measure the change of the Earth's magnetic field at the surface.
Really? So I didn't know that. I didn't know either of those things. I mean, it makes sense.
Okay, we're going to take a total aside here because this is really important then.
Let's go down a rabbit hole here.
Yeah. And let's go back to the Second World War again as well, because might as well. This is actually where this story starts. And it's kind of important to understand, I guess, where modern geophysics and geology is today. So just throwing this out at you, what's one of those things in the Atlantic that was really important that the Allies learned how to do?
In the Atlantic in World War II? Navigate. I mean, there was like a lot of submarines going on around that time.
Bingo.
Yeah. Okay.
So you had to find the submarines.
Okay.
What are submarines?
They're
hunks of metal that are underneath the water. And so they actually designed something to measure the Earth's magnetic field as a portable unit specifically to find U-boats.
Interesting. Okay.
And so, I mean, a lot of technology gets built because of war. And eventually in the late 50s, I think, they started towing them behind ships, not for war purposes or finding U-boats, but actually mapping the sea floor. And you found these stripes along the sea floor of magnetic field, or the rocks having magnetite, which is an iron mineral, with its domains pointed in the same direction as our current magnetic field and the opposite direction of the Earth's magnetic field. And then it would repeat. And it would repeat on either end of what was a spreading center. So plate tectonics, where we have two ocean plates splitting apart, we call that a spreading center. But before we knew what those were, we were able to prove that they actually spread by measuring the magnetic field across. And so the Earth's magnetic field changes every so often, about every 400,000 years or so. It actually completely flips. And so this is baked into the rock record.
So north becomes south and south becomes north?
Magnetically, yes.
Magnetic south and magnetic north?
Yes.
Wild. And so you keep going. I think there was more to that and I interrupted, but.
Yeah. So this whole process of finding this data set, showing that the Earth's magnetic field flips, showing that these patterns radiate out from these spreading centers in the middle of the oceans, is the basis for plate tectonics. We know plate tectonics today. The modern sense of geology came about really because of this technology.
Which was because of the U-boats.
Yeah, I mean, we had magnetometers before, but it sped it up, right? Like it's all these things. It's like, even in a vacuum, if that didn't happen, I'm sure we would have got there eventually, all things considered.
Sure.
But would it have taken us an extra 50 years, 100 years? Who knows, right?
Wow. All this stuff. So tell me if I'm understanding this right, but it sounds like a good amount of the technology that we're using today, to understand earthquakes, plate tectonics, comes because of World War II. So before that, we were using pretty rudimentary stuff. Am I getting it right or no?
I would say it's a lot of stories can come back to these great leaps in innovation. Mm-hmm. And I think we can make the same story about right? With the changes of the internet and how things spun out about that. But in World War II was just one of those really big instances where we had this great increase in innovation because we had a bunch of problems to solve and threw a whole bunch of money at it.
Makes sense. Yeah, that's fascinating though. I had no idea. There's this stuff that, you've been learning about, or I've been kind of, let me rephrase that. There's this stuff out there that's just around, right? And you kind of assume that it's just always, to me, it's always been there because World War II is not effectively, World War II is before my time. And so like, I don't know. I appreciate you taking the time to go down that little rabbit hole with me, man. That's really cool. So yeah. So within one of the questions I was wondering was around the definition of, you already talked about what a geophysicist is, and a volcanologist is just within that another subset of someone who studies what volcanoes are. So you're a geophysicist who studies volcanoes.
I mean, that's what my degree was. I say today I'm more of just a geophysicist, but volcanologist by training. So I would look and apply geophysics, or the physics of the earth, generally speaking, to volcanoes.
Okay.
So in my case, I'm looking at changes in mass. So again, same idea as measuring the Earth's magnetic field. You can measure the Earth's gravitational field, which is another subset, which you can say is geodesy. So we're measuring how the Earth deforms and mass movements within the Earth. And volcanoes are one of those things that move mass, right?
Yeah, that's a good point. So, by the way, you mentioned gravity, and something I was curious about. I don't know if we can get to this later or now, or if you have any thoughts on it. But do we know much about gravity? Like, we know it's there, right? It's kind of always assumed a constant, but do we know much about gravity?
I mean, yes and no. Like a lot of things in science, the more you get into the weeds, the more things become messy.
Okay.
So when we start dealing with on a day-to-day basis, like our lives and how we interact with the world, we know exactly what gravity does.
Sure.
We know exactly how it works. We can predict everything. When you start to get down to like, what is the cause of gravity? Things get a little bit more weird. So if we think about magnetics, we can think, well, charge. We can measure charge and we can see the buildup of charge. So we can see a magnetic field or an electric field. And likewise, we can find particles that represent the other forces. But there is no found particle as a force carrier for gravity. And so, well, yes, we know exactly how gravity works in our day-to-day lives, but when we really get down into like the messy details, the very minutia of it, we don't have a real good grasp. And I think that's like one of the biggest holy grail type things that may actually fall in our lifetime is trying to figure that out. Who knows? I mean, these types of leaps come almost without warning. I mean, in retrospect, you can see them, you can see how it led up to it, but there's like this final leap in logic that has to come to be able to bring it all together. And who knows when that next general relativity type theory comes out and really starts to make us understand like the finer bits of what gravity is.
It's fascinating because it's one of those things, like you said, it's one of the systems that it affects us all the time. I like the way that you described it, that we understand how it works and it's constant, but I also like the comparison to missing like a molecule or, some sort of energy that we can actually measure and understand the source of it. Are there any like working that you know of, like any scientists that like have well accepted or regarded potential hypothesis for that? Or is it kind of just like, there's a thing out there and we all know it's there. Let's hope it doesn't turn off or turn on or change or anything, but it's just kind of how it works.
Well, yeah. So, I mean, one of the main candidates is, I think, what's called the Higgs boson. So now we're really getting into particle physics, which is kind of outside my expertise, but that's okay. I don't mind making a fool of myself in every part of science.
You know way more about this than me already. So, like, I'm going to believe it. And, let's just assume that all the listeners are going to believe it too. So,
or they'll send you angry fan mail, but that's okay.
Yeah, please feel free.
But yeah, there's other things that are out there. So trying theory is another one that's trying to bring gravity inside what we already understand the other forces to be and inside to like bring it into quantum mechanics, because gravity and quantum mechanics doesn't work very well. We know that's a problem. And so until we have quantum gravity and it can, then expand out to what we can measure in the universe today, it's like a big hole. So there's a lot of, I like to call them theory or hypothesize, because we don't really have strong data to support them. But there is a number of different ways of looking at it. And it's entirely possible that our basic understanding, or I should say our assumptions, excuse me, in cosmology are actually wrong, that gravity is perhaps not invariant over time and space. It's possible. We have no way to prove it. Everything we have done so far suggests that it is. And so we don't have any data to, you know what I mean? Like there's lots of we don't know. And dark matter is a good example of gravity at large scales that we can't fully explain. Now, there could be particles out there that can represent mass and gravity and can explain all of these things, and our standard models stay safe. But it's also possible that their standard model and how we think of the universe today is just fundamentally wrong.
It's interesting you mentioned consistent across time and space, because I was just thinking while you said this, it's been constant as long as we've been tracking and measuring it and understanding it and have record of it. But I mean, we don't even have that. Our record's pretty small in the grand scheme of things. And so we're looking at a big data set for us, but not for gravity. That's interesting. We do. This is such a dumb question, but I'm going to go ahead and say it myself. I think I know the answer, but we know that it's like it's somewhat localized to our Earth or to mass in general, right? It has to be or does it? Because I'm just thinking, okay, I'm regretting even saying this topic already, but like gravity's different in space and it's different on the moon than it is here. And so like, it's got to be something within the Earth, right? At least we think so, unless it's
no.
No?
I mean, yes and no. Yes and no. It's all about mass. It's just mass. And just how much does that mass, if I want to use the relativistic or Einstein's theory to explain it, its mass is bending space. So you can think of you're falling into a potential well. It's more like energy. It's much easier to show. There's some great demonstrations on YouTube where they stretch a fabric and kind of show you what happens when you put something heavy in the middle of the fabric. It sinks.
Sure. Yeah.
And so that represents like the gravitational well. You're bending space. And so you actually reach a lower energy and everything wants to be at its lowest energy. Everything wants to roll downhill. And so gravity represents kind of like that towards the bottom of the hill.
Oh, fascinating.
Okay. So in the case of the moon, it's less because there's less mass.
Sure.
And we've measured gravity on the moon. We've got things, orbiting it. We can calculate it to very, very high precision. The force doesn't change. It obeys all the same things that we have here on Earth. But we can't say that for certain 10 billion years ago or 13 billion years ago. Sorry, when the universe is really, really young and really, really hot and really, really dense. We make the assumption that everything that we understand today, all the forces behave the same way today as they did then. And they probably do. Don't get me wrong. I'm not saying that what we know is completely wrong. It's just, it is an assumption that's baked into how we understand the universe at the moment.
That's freaking so cool. Thank you. Thanks for going there. I love this kind of knowledge. Because and a little bit of something about gravity, I'm assuming, right? So one of the things I was reading about is that you were using gravimetry. How am I saying it wrong? Gravimetry?
Yeah, gravimetry.
Thanks, gravimetry. Yeah, you're using gravimetry. That's a great word, gravimetry. Yeah, you're using gravimetry in some of your work, which is what?
Well, that was the majority of, I would say, a lot of my master's and PhD was using gravimeters to measure the changes in the Earth's gravitational field at volcanoes. So we're coming back to volcanoes and the fact that volcanoes you put mass in and sometimes it erupts and mass comes out. Mm-hmm. Or you can get things where density changes. So if you have a large magma body and it's close enough to the surface, it will passively degas and lose mass, bringing carbon dioxide and stuff to the Earth's surface. Well, that loss in mass can also be measured by gravity sometimes. You can have collapsing of bubbles in the magma chamber, causing a densification. You can have, like, all of these things change mass. And then you have the complication of actually groundwater and hydrothermal fluids as well. When they move around, they change mass as well. So gravimetry is just one possibility to try to look at these dynamic systems. I also did what we call Bouguer gravity, which is a bit more like a snapshot in time. So you can repeat measurements in the same spot and look how mass changes, or you can map how the gravitational field changes. And as long as you correct for things like elevation, position on Earth, now you end up with a map that will correspond to changes in density beneath your feet.
Which will impact actually the gravitational pull or force at a measurable amount?
Yeah, but measurable is different than being able to feel it.
Sure.
When we talk about like 9.81 meters per second squared, which is the acceleration due to gravity, that's what you feel standing on the Earth's surface at sea level. We're measuring something like 10 to the minus 6 or 10 to the minus 9 of that. So we're talking about something so minute that an average person will never, ever feel. Like, it's just way too tiny. But it's enough that these really sensitive instruments can measure them. And so you can detect changes in density beneath the Earth's surface. So one of my favorite papers was actually on Mauna Loa to the Nanoli Hills. And so, boy, I take a deep breath because now we're really meandering across science, and I don't want to lose your listeners or you in any of this. And we haven't really fully built up to it because I don't know where to step the ladder.
This is how this conversation goes. It's meandering. It's all right. This is good.
So if you understand that we can measure changes in density, or at least locate where they are by measuring the Earth's gravitational field. Volcanoes are very dynamic. They have a lot of different things that are associated with them that changes density. For instance, if something cools beneath the Earth's surface, it's much denser than stuff that erupts onto the Earth's surface. Because once it erupts on the Earth's surface, all the gas comes out of solution and you're left behind with bubbles, which are voids, which are essentially density of zero-ish. And so your effective density of the rock there is much less because you get all those voids. But at the core of Hawaii, because there's so much volcanic activity, they ends up with these very dense cores. And the reason for this is because of olivine. Do you know what olivine is?
No, I have no idea.
Okay, it's a green mineral. It's almost a semi-precious gemstone sometimes. I think they call it peridot.
Oh, I
It's
know.
green.
Yeah, no, peridot. Yeah.
It's green, right?
Okay. Yeah.
Yeah, it's an olivine, and
Okay.
it forms in the basaltic lava that Hawaii has. But it tends to be it's quite dense as a mineral, and so oftentimes when you have a magma chamber, they settle to the bottom.
Okay.
And over hundreds of thousands to millions of years, lots of these olivine crystals settle to the bottom of the magma chambers of Hawaii, creating this very, very dense core to the volcano. So all the major rift zones and summits of each individual volcano have these quite large gravitational highs over them. And so one of the spots that I thought was really interesting in Mauna Loa is they have this area where the rocks are significantly older than everything else around it by like 127,000 years. And that's really surprising because first off, the Earth is 4 billion years old. That shouldn't be surprising normally to find all of a sudden this little area of rock is 100,000 years older than the rest because geologic time's so big. But when you think about it on Hawaii scale, when you look at Mauna Loa, it's like 90% of the volcano is less than about 7,000 years or 14,000 years old because it repaves itself. It just erupts so much that it keeps burying the old material. And so now you have these little pockets on one particular side of the volcano, which is older than everything else. And so the question is why? What are these things? How did they survive not getting buried?
Yeah.
And so there was some suggestions or hypotheses of what they are. And I thought, well, gravity should be able to do that. And so I got permission as part of my PhD to go out there and collect this gravity data.
That's not a bad yes to get, by the way.
No, yeah. I mean, something I wanted to do. I was super fascinated with it. I'm like, I want to solve that problem.
Yeah.
And it's getting a chance to spend time in Hawaii, walking around in the lush jungles and stuff.
Yeah.
It was totally worth it. Definitely no complaints.
Yeah. I respect the strategic planning there big time. Yeah.
Well, when you live in Canada, we don't have too many active volcanoes. We have some that are potential part of the Cascades, but let's not get too sidetracked.
Sure. Okay. So you're in Mauna Loa. You get the yes, so you're there. Yeah.
Yeah. And what I noticed, what the data showed was that the area that is called the Nanoli Hills, these hills or little bumps, if you want to call them, they're not mountains or anything, that are much older, sit on top of a gravitational high. Now, these types of highs only get built if you have significant long-term volcanic activity underneath it. It's those olivines accumulating, right?
Okay.
And so that I could rule out that it wasn't part of a proto-Mauna Loa. It wasn't a summit of a volcano or anything. So that means it had to have been the rift zone of Mauna Loa. But that's not where the current rift zone of Mauna Loa is. So how did the rift zone go from where the Nanoli Hills are today to its present location?
And a rift zone, just so I'm clear, I want to make sure I'm tracking here. A rift zone is the opening in the Earth. Is that right?
Yeah, it's an area where the Earth is splitting apart and magma can come up underneath and erupt.
Okay.
And so the either side of the rift zone is moving apart from one another.
Got it.
And we say the same thing when we talk about rift zones in the ocean, where you have two oceanic plates moving apart.
Okay.
So I went through a lot of humming and hawing about how to solve this problem because you can't just have an abandoned rift zone. Something had to have changed. And the most likely candidate, based on timing and evidence, was landslides. So Mauna Loa had these epic debris flows. It's so astronomical to think about how big these are. They're in the order of over 100 cubic kilometers of material moved off of Mauna Loa around 114,000 years ago. And so, yeah, it's
That's
a kilometer is a really
insane.
far. So it's like a kilometer by kilometer by kilometer plus over 100 of them. So these are absolutely massive.
Yeah. Keep going.
And once you do that, once you remove that much mass from an edifice, you're going to change the internal stresses of that edifice quite drastically. And there are other volcanoes where this has been noticed in the Azores. You might have heard once upon a time ago that they're worried about a mega tsunami from the Azores as a big collapses into the sea. It's a real thing. You can look it up. It's mostly overblown. It can happen, but not mega tsunami. And we can get into the reasons why in a moment if you want. But so what happens is the rift zone, because the forces have changed, it migrates into the landslide scar. And so it gives you a way to geologically provide an instantaneous mechanism to move the rift zone. And I put geologically, if you're listening through headphones, in quotation marks, because it's not going to be instantaneous. You still have abandoned magma chambers that can erupt on the old rift zone. So it likely is going to take a handful of years, but geologically, you'll never notice what the difference is, right? To our eyes, looking back in time, it's instantaneous.
Why is it instantaneous to our eyes?
Well, just think about for our eyes, because what's our resolution in dating something that's
I see what
about
you're saying.
100,000 years old, right?
Yeah, good point.
We can't see the evidence of how that happened, right?
Yeah,
we're trying to build it out from a handful of rocks and some dates, and everything else has been buried. Remember, the surface of the volcano is very young geologically.
Sure. I see what you're saying. So it might have taken this to happen. It might have taken it, let's call it, I'm making this up, obviously, but it might, I like how I just said, I'm making this up as if I would otherwise have the fact. No. So it might have taken, even 10,000 years, but it's effectively, even if it wasn't, but effectively it's instantaneously, because we don't know if it took a year or 5,000 years or whatever it was, or 5 minutes. It just wasn't. It just happened. Yeah. Okay.
Yeah. Because the pathways need to be rebuilt, right? It's going to migrate in. And so that process, like maybe the rift zone doesn't erupt for, 50 years or 100 years or something until it makes the full migration. We don't know. We weren't here.
Sure.
We can see things in the rock record. We don't see a landslide scar because it's been buried by further products, but we do see the debris flow run out in the ocean. So you can go with bathymetry measurements and using sonar and stuff to map the sea floor. And that's where you see the run out distance from these massive, and I do mean massive landslides. There's so many along the Hawaiian archipelago. So that was one of the major things about the paper that I thought was really interesting, is that we see these landslides on the ocean floor. We see them around these large island volcanoes. And Hawaii is not the only one, but perhaps this happens more regularly than we give it credit for, in part because they get buried. Anything that erupts that much, you're going to lose a lot of the evidence for it. And so,
yeah, that makes sense, especially on an island like that. I mean, tell me if I'm misreading this, but I mean, I'm thinking if it blows up, someone's going to go out in the water. You're never going to see it again, right? And then it's going to get covered up the next time it goes over, and other things are going to happen to it. Is that
more or less? Except it's the stuff in the water that we can still kind of see.
Oh,
it's
really?
The stuff on land that's all completely buried, because the stuff in water, once lava really hits the ocean, it kind of falls apart and has to build out and then build out and then build out, and that's quite a slow process. Whereas on land, it can travel quite a distance because it's runny, it's not getting cooled the same way. And so stuff that travels out over the ocean floor off the edifice generally can get preserved for a long period of time. And that's partly the reason why I was able to, I think, fully break down this little tiny section on the island. It was really cool and a really fun project.
That is cool. So were you able to do, what kind of data were you able to gather, kind of firsthand data while you were out there? Were you getting new stuff, or were you just? Yeah.
Well, I was collecting the gravity data that I used.
Okay, the gravity data.
So that was primarily, but I also got to use a bunch of other data to build the picture, right? And the Hawaiian Volcano Observatory was there, so I was working with the USGS. There were some as co-authors on the paper as well. And they were instrumental to making sure that I got the other data I need to put it together. And that includes seismic, that include island-wide gravity survey. So that provided the ability to remove the effects of other deep-seated features under the volcanoes. Again, they're very dense, and you don't want the signal from that very, very dense thing to wipe out the signal of something shallower. So using a much bigger data set that can truly understand or give you some kind of constraints on what that is, and then remove it from your data set, for instance.
That's cool.
Yeah, it's solving problems. That's what science really is when you get down to it, right? And sometimes the problems are just fun to talk about and really cool, like this one. Sometimes they're, life-changing, like vaccines, and sometimes they're just weird and quirky, and you have no idea where they're going to go.
But they're all probably unique to discuss and dissect. How did you come across this in the first place? How did you learn about this? Was it like...
Yeah, so we got to go back in time a little bit, I guess. So I spent a lot of time in Hawaii. So I was one of those, I was really good at geology and had some problems with the upper level math. Physics was okay for the most part until it got like, you need this prerequisite. Well, I don't have that prerequisite. I'm in geophysics. And they're like, well, you're going to find this tough. And you're like, oh my goodness. And so I needed a way to get into grad school to, not that I had terrible grades, but I didn't have a 4.0 average. Like, that's just what it was. And so I saved up money traveling across Canada's Arctic, collecting geophysical data for mineral exploration, and then used that money to get to Hawaii to be a volunteer at the Volcano Observatory there.
Okay.
And back then, before the whole summit caldera collapse and stuff, they were running international volunteers all the time. And they had a house inside the park that the volunteers would stay at. It was amazing.
Oh, nice.
Yeah, so I got that experience, volunteered in Nicaragua at Masaya Volcano, and then got to grad school. So I was already quite steeped in Hawaii and its ways of doing things because I was a volunteer there twice. And then I got to go back on my master's to collect gravity at Kilauea. And then I convinced them to allow me to go collect data somewhere else.
That's cool. So you paid for this by, it sounds like you paid for this, you said gathering gravitational data for mineral exploration, mining companies, I'm guessing, right?
It wasn't just gravity, but yeah, I did a lot of gravity that first summer. So it was like, okay, I don't know how to explain this, because if you spend a lot of time working in the woods, truly in the middle of nowhere, like as a tree planter or something, maybe you understand what I'm saying. But the vast majority of people, this is completely wild for them, where you are hundreds of kilometers away from the nearest road, town, whatever. You're flown in sometimes by float plane or float plane, then helicopter to this little tiny camp that is canvas walls and a plywood floor. And you're there for 4 weeks to, depending if you're a geologist, I didn't have to do this, but geologists might be there the entire season. So that's like 3 months straight. I was never in one place longer than about 7 weeks, but, and yeah, you just work every day. It's like going on a hike, carrying stuff every day for 6 weeks straight. I mean, you got to be in good shape. I'm a little out of shape now, but back then,
If you're not in good shape at the beginning, you are by the time you're a few weeks in, right? I mean,
yeah. You either crack, and I saw lots of people crack, or you somehow manage to deal with it. And sometimes the ones that crack are the ones you're like, you should be fine. You're fit, you're strong, and then they just can't handle being isolated with a bunch of weird people in the middle of nowhere.
What an adventure, man. Why do mining companies care about gravity?
So again, density. So there's a number of different things when you're looking for minerals, and we need the minerals for our modern day comforts, right? From computers to everything. And some things you find based on their physical properties. And some things it's because they're dense. Some things it's because they're conductive. Some things you use magnetics, for instance, you measure the Earth's magnetic field because magnetics gives you a really good idea of structure. So you combine all these different data sets, including just going out and hitting rocks with a hammer and writing your observations. You combine it all to try to find where these deposits are. And the entire industry is built off of, I guess, a lottery system almost. Because you go out, you try to find your thing, you raise a bunch of money, people buy stock in your company, and then you spend that money to hopefully find a mine, but chances are you won't, and then you'll go belly up, and then everyone loses their money in the stock, and the process repeats, right? That's kind of how the whole thing works.
That's so wild.
Very simplistic. It's more complicated than that, and it's better than I'm making it out. I'm a little jaded on it because I work in this industry, but it kind of feels like that sometimes.
That's
But nevertheless, you're taking data. This is the part that I actually like.
wild.
And then trying to figure out and piece together the earth, try to understand the earth and look for those minerals that are required for a modern life.
Wow. I mean, not that much has changed since, Wild West gold rushes, sounds like.
Lots has changed. Thank goodness it's changed. Even the people in the field have changed. And I don't know if it used to be a really much more rough and tumble atmosphere when I first got into it. And that was like 2007, 2006-ish.
Okay.
And there were still stories from the 90s of hiring guys right off the street. If they didn't have a DUI, they were hired. It didn't really matter any other part. It was like, you can work, you're willing to work out in the middle of nowhere, and you can drive a car, you're hired. That was it.
Let's go.
That was it. Like,
wow.
the people that were there were really, really rough.
Okay.
And today it's much more like the young adventurous types that just want to work hard and have fun doing it. And so you get to see some of the most amazing sights. Like, I don't know what to say. Like, you're up above the Arctic Circle on a little island. I mean, yeah, you have to carry, some shotguns for polar bear defense, but like the things you see out there, the rocks, the wilderness, the animals. I had a wolf come by and pick up a bundle of sticks, that we call them lath, or you put them in for pickets to measure distance. And he picked it up, carted it off, and then rolled around on it like a dog. And you're just like an Arctic wolf, just a lone wolf in the middle of nowhere. And you're just standing there like, okay, did that really happen?
Watching it. Thinking
Just
that
watching
thing,
it.
That thing doesn't try to take me out.
No, I wasn't worried. But not for the wolf. I mean, if I started seeing 3 or 4 of them, then probably I would. But a single wolf? No, that's okay.
That's
Polar bear? Of course, no.
Yeah, of course you're going to be terrified of that one. But I mean, like, you get to go places where maybe a handful of people ever get to go. If you're getting flown in there and then hiking out, there's something about being able to experience something like that, and just know that, hey, there's not that many people that really ever get to see this and experience it. And I think that makes for an amazing experience. Even pictures, after the fact, there's nothing like being in a specific experience. So
yeah,
that's cool.
Yeah.
I love that you did that. I think that's really cool. Did you ever have any run-ins, like dangerous run-ins with animals that you're worried about, or was it most like, oh, well, they kind of left us alone?
Well, I don't know. There's a few times where I was a little weirded out by bears that didn't really care. They were just curious and not scared of me at all. And you're just like, I don't know how to take this because I don't know what they're thinking. Because as soon as they believe you're food, that's when you run into a problem. Up till that point, as long as it's not a territorial thing, they're just checking you out. They're trying to figure out what you are.
Sure.
I think my 2 scariest times were actually not with what normal people would call dangerous. Once was with a moose.
I've heard those things can be really...
They're huge. That was more the thing. They're just so massive. So I was actually doing gravity in the Yukon in this nice, beautiful valley. It was so gorgeous. This big U-shaped valley on like a river plain. And there's this creek ditch or drainage. But it's not drainage, but some kind of flowing water beside me. And I'm walking, and all of a sudden I hear this big loud noise, and this big moose with her calf just comes right out from underneath me and walks away. And I'm just like, if it came at me, there's nothing I could do. There's not a thing I could do. And because it had a baby, there was a real possibility of that happening. Like, it never came at me. It went away from me, as most animals do. But if it had thought it was threatened by me, I don't know.
Toast. Yeah.
You're toast. They're too big.
Yeah.
You're not going to fight a moose.
Yeah. Yeah.
You're not going to fight a moose.
So, I mean, what's like the guy, like when you go up in a situation like that, they give you a briefing ahead of time. Like, if you encounter a moose, I mean, what's the guidance? You get quiet, make yourself small, try not to be noticed? Or is it like you try to let them know that you're there and then just get out of their way or stay out of their way?
Mostly the latter. You're not trying to challenge a moose.
Of course, yeah. It's not like make yourself bigger, because that's not good. You're not going to intimidate that thing.
No. And you're really trying not to be a threat, because it's not trying to eat you, right? So it's more like you're trying not to be a threat to it. So it's a little different. However, if it's charging you, you're better off trying not to move in straight lines and to go into the trees and try to climb.
Yeah, they can't climb like a bear, right? Yeah.
Yeah, and you got to be on a thick enough tree that it can't knock it down. But I've never been in that situation. I don't think I've personally known anybody in that situation. I know people have been charged by moose, but they didn't have to climb a tree. They got into a car or something like that. We're okay, right?
Jeez.
Yeah, moose are kind of scary. The other time was kind of disconcerting. Was again, I was doing gravity, but I was doing it for looking for diamonds out in the, again, Northwest Territories, and an entire herd of caribou came through, like hundreds and hundreds of animals. And if I didn't keep dancing with my hands above my heads and just constantly moving, they would have just ran right into me.
Really?
Just because there's so many of them. Like, you're literally inside a moving herd. And I was like, wow.
I mean, I don't know how big is the herd? Like, are we talking like a dozen or like, like a
So
couple
in
dozen?
my case, it was a couple hundred to maybe 1,000 animals, but some of these herds can be in the tens of thousands, depending on the time of year and stuff. Now, it wasn't that big of a herd that went through my little survey block, but it was definitely hundreds of animals, no doubt. I do not know how many.
And when they're moving, I'm guessing they're just running. And so it's not like you have a bunch of notice. All of a sudden you're doing something and there are caribou all around you.
Yeah, they're running, but it's not like a stampede. They're not going full out, right?
Okay.
It's more of a canter, I guess. So if a bunch of horses are cantering towards you and they're not spooked, generally speaking, if you move about, they're going to move around you, right?
Mm-hmm.
But it was just a surreal experience to be completely surrounded by a herd of caribou.
Yeah, that would be surreal. I can't think of a better word for it. That's crazy. Wow. And did you find any diamonds? That's also what I want to know.
Well, there was already a diamond mine there. We were like doing exploration on the rest of their property. So I'm sure they found diamonds somewhere else. It was not really my concern. I never got to see the diamonds there. It was very high security, and
sure,
it was always
sense, yeah.
It was always weird to work out of a mine site, actually, because you go from basically almost cowboying it, where it's, you have health and safety. You do. But there's just a different level of health and safety and rules and regulations on a mine site. And actual fact, most of their policies say we're not allowed to do what we're doing. So you have to find a way to fit into a square hole when you're not square. And it's always a weird cultural tug of war, and I never really enjoyed it.
That are most of these places pretty remote? Like, you got to fly in or get truck.
The diamond mines in Canada are.
Yeah.
But there are a lot of mines that you can drive in. Ideally, that's what they want, right? They want a road to go in so you can get all the ore back out. But diamonds are light enough that you can get them out, right? And so you don't need a port. You don't need, you just need an airport. You don't need a deep sea port or something like that. So it works for them.
That's cool. Yeah, you've worked in some unique areas, and I'm thinking like industries and actual physical areas. That's pretty cool. Yeah, I like it. So, all right, let's see. So tell me about the transition out of being, working in the field, to where you are now. How did that come about?
Oh, I think you actually have to start where the postdoc ended. In a roundabout way.
So back to Mauna Loa?
No. After that, I was actually doing a postdoc, an industry postdoc, looking at diamonds and geophysics at a set of potential. Well, it did open as a mine. I think it's closed down now in Quebec, but I was working in British Columbia. And after that kind of finished, I was trying to get a job in academia as a professor, and I just couldn't quite manage it. You got to remember, we produce way more PhDs in North America than there are professorships.
Sure,
it's crazy in a good way. I mean, it sucks for the one who wants to stay in academia, but it's hard when that's what you want to do. Yeah. And so I needed to make that transition back to industry. And I was stuck in a position because in Canada and in lots of other places, geophysics, geology in general is actually a regulated affair, much like engineering or even lawyers. They're different, obviously, but we are lumped in with the engineers here.
Okay.
And so you need to have a professional designation to do a lot of things with high responsibility. So although I had a PhD, although I had some experience in the field, I did not have enough to be able to get my professional designation. But I also was having a hard time finding a job because I had a PhD, but not a PGO. So I was a PhD, so overqualified, but yet not qualified enough.
What's a PGO? Sorry.
Professional geoscientist.
Okay.
So it's like being a professional engineer.
Got it. Okay. So you have the PhD, but not the PGO. Got it.
Yeah, so you're kind of stuck in limbo, right? So you're overqualified, people don't want to hire you, but you're underqualified for other jobs. And so you're stuck in this middle thing. And so I called up, I sent an email, resume off to somebody, and he calls me up and he goes, "Do you actually want to work for me?" And I remember thinking, and I said what I was thinking at the time because it just caught me off guard. Well, I sent you a resume, didn't I? And so he hired me as a geophysicist, collecting data in the middle of nowhere, and did that for a couple of years.
And when you say collecting data in the middle of nowhere, these are kind of the stories you were telling me about just now, right? Okay,
yeah,
okay.
It's maybe not the exact same because I did this a couple of different times in different places. So I'm mixing and matching stories from different time frames,
Sure.
but
Okay.
nevertheless, it's the same work.
Okay.
And then after a while, essentially, there's no other way to say it, that my mom passed away
Oh man.
and used a medical system here called medically assisted dying. A long story short, it was kind of a brutal affair having to deal with that. And I really wanted nothing else but to get back out to work, to just kind of leave problems alone.
Yeah.
Except I was taken off salary at the same time, figuring that I wasn't going to be able to get back into work because I couldn't manage it or something. And I was like, you got to be kidding me. I got kids, got bills, you're going to take me off salary. So now I got to find a new job. And the one I got just kind of opened up at the exact same time. I had the interview 2 days before my mom used the medical assisted in death. And I managed to get that job. And life's laughing in some respects. Like it ended up really working out in a lot of ways, which is weird. But it's like one of those things, no matter what life throws at you, if you are tenacious and willing to put yourself out there, sometimes it works out. I mean, it is a bit of a survivorship bias mentality, perhaps, but it is still true that you have to do that if you want to succeed.
So, first of all, thanks for sharing that and going there. I think every single person I've talked to so far in this podcast has had some sort of reinvention. And that's a very common, I think what you just described is a common thread. And to your point, like, okay, I see what you're saying about the survivorship, and not to like completely, I'm not trying to argue with you at all. I also will just say that, like, I guess the reality is, like, what's your choice? You can either adapt and try to move on and try to reinvent yourself, or you can just be like, well, this sucks, I guess I'll give up. And so if you're not a give up kind of person, then what are you going to do? And you did it. So, yeah, I'm really curious about this, by the way. And by the way, I'll edit this part out if you want. This is fine. I'm going to ask you, totally okay to say no. But I'm interested, again, I'll edit this out, but I'm interested in your perspective on the medically assisted death. I think I've been hearing about it, and it's legal some places in the States. And so, but I mean, I've never heard about it from the perspective of someone who's been a loved one, or even remotely close to the person who died.
Yeah, I mean, I think it'll be okay. I don't think I'm going to get myself too over my skis here, but I am going to be careful in how I talk about this. More broadly, I think it's a good idea. In a broad sense, maybe not broad, in a narrow sense, I think it's a good idea. Let me rephrase that.
Sure.
Because when you are at a stage in life where it isn't possible to succeed, and you know that there's just certain laws of nature that isn't there.
Yeah.
And you're basically saying, I'm going to take this time now instead of dealing with the torture that I wouldn't wish on my worst enemy. And there's a medical understanding that that is what it is. You know, doctors have signed off on it. The science proves that it's actually a really good program. Where the program tends to fall apart is where it's been broadened here in Canada. And even then, you have to take that with a grain of salt. But there is a number of people, and I would put my mother among them, who choose to use the program in ways that it's not, I would say, was not in the spirit of how it was originally designed for. So let me be clear. It was my mother's choice to use it, but she also did not have a condition that was significantly worsening over time. So it was her choice. In the end of the day, she was happy. And I guess that's all that matters. I'm uncomfortable with it because there was no reason for it.
Yeah. That makes it really hard to accept, I bet, as
I
the
mean, you
ones
could
left
argue
behind.
there was a mental reason for it,
Sure.
but it has of yet not been broadened to those with mental health problems.
Hmm.
And that is kind of the next stage in the rollout of that program. And I would say lots of people are concerned about it, given there are problems now. I'm not saying they're big problems. I'm not saying they're systematic problems. I'm not like, at its core, what it's trying to achieve is right.
Yeah.
I feel that deep in my heart that it is right what it's trying to achieve.
Yeah.
It's just like any program of any sort, there is potentials for people to fall through the cracks or to choose to use something in a way that wasn't really thought or designed in that way.
Yeah. And the spillover benefit of that, or not I'm sorry, the wrong word. The spillover impact of that is that people, they're bystanders who get impacted in a situation like that and have to deal, or, left behind, so to speak, with the hard parts. And that's
Sure,
an
but
extra hard thing.
if it was used correctly, and let's
Mhm.
be clear, if it was used correctly, those people are going to leave this mortal coil anyway. And so those
Okay.
people are going to be
Got it.
left behind anyway. And so it's not,
I see what you're saying. Yeah.
yeah, like I said, in the way it's in the spirit of it makes sense. And it really does. And I would say that there's lots of data, particularly from Europe, that shows it's actually easier on the grief of those who have to deal with it.
Interesting. I didn't know that, but I believe you.
Again, there's caveats in here. Those systems are a little different than the Canadian system, et cetera, et cetera, et cetera. But when it meets those criteria where somebody is under severe distress physically, where the loved ones are having to deal with all of that horribleness at the same time, having that opportunity to pick the time is actually really, really good thing.
Well, I have never been through that. But I appreciate you being willing to share, like, just thanks for going there and sharing your perspective on that. So at the time, then this thing kind of should happen. Like you said, like the things worked out, and you landed this new opportunity, but it took you out of the field. And so is this close to where you are now in your career, or?
Well, I'm still in the same job. I mean,
Okay.
Sure, that position has changed and evolved a little bit over time as well.
Sure, yeah.
But now instead of collecting the data, I'm taking data that other people have collected and then creating 3D models of the Earth, tracking those properties. And so it's one thing
That's
I've
cool.
kind of danced around and not really talked about, but when I'm mapping out the Earth's magnetic field, the gravitational field, or what have you, you can actually take that data and using some assumptions, create a 3D model of the Earth showing where concentrations of those properties change.
Interesting.
So you're building a 3D model of the Earth. Call it an inversion. You're inverting the data. And so in the case of when I was talking about density, I would take a gravitational map and that data and then create a 3D model of changing density. And so now I'm doing that on a day-to-day basis to provide value added for the companies that are looking for those shiny minerals underneath the ground. And sometimes the project is really cool. I get to take multiple different data sets, incorporate the geology, and really play the sort of geologic sleuthing or detective work of trying to figure out what's happened. And so in a lot of ways, it's much more academic now than it ever has. But at the same time, I also have a much more free time because I know when I'm going to be home.
Yeah.
Before I couldn't buy, concert tickets. I couldn't go to see a band play. There was at one time I made it my New Year's resolution to go see a concert. And it took me all the way to, I think it was November or late October to go see a concert. And I had failed two times.
But you did it, man.
I did it. It was kind of an odd concert to go by yourself to, but that's okay. I don't know it's a punk band, Me First and the Gimme Gimmes.
Oh yeah, I've heard of them. Yeah, I couldn't tell you one of their songs, but I know the band.
They're a cover band. That's what they do. Is they cover songs and they make them punk.
Nice.
But at any rate, it was just one of those random things and so all of a sudden I have this ability to do this free time. I can plan my life. I can coach my kids' soccer games now. Like I couldn't do any of that kind of stuff before. And so to scratch a little bit more of that academic itch that I've been missing, I started Whimsical Wavelengths.
I like it. I have a couple questions before we move to whimsical wavelengths. It's okay about the gravity stuff.
Yeah, absolutely.
So my first question is something I saw just recently. Like I saw, I don't know, some like a short documentary clip online about like these places in like I think this is like in West Virginia in the States, like one of these gravitational anomaly places. Do they really exist where like gravity doesn't act like you think it's supposed to act? For example, like in this one, it was that like a gravity hill, you know, for example, where the ball will actually roll up the hill. Is that legitimate, or is it just some, you know, tricky filmography?
It's mostly an optical illusion.
Okay, fair enough.
Gravity is gravity. Here, I thought you were going to talk about like LIGO or something like that.
What's LIGO? I don't know what that is. Maybe that's it. It sounds like there's something there. Tell me.
I don't actually know where it is. I just know it's in the States somewhere.
Okay.
Where they're trying to, or not trying to, they are detecting and measuring gravitational waves.
Like,
so again, we got to go all the way back to the whole premise of what is gravity. And so when Einstein came out with his theory of relativity, he said gravitational waves should exist.
Okay. But we've never been able to measure them.
But he also said we'll never be able to measure them. And lo and behold, we have been able to measure them. And what's causing them, as far as we can understand, are black hole mergers. And that's where two black holes are colliding. And then you can actually measure through these kilometer-long lasers, I think is what they are. Don't quote me on that, but I know they're very long distance between, so you can measure minute changes. And yeah, they ripple the fabric of space and time. And so you can actually pick up these gravitational waves. So
there's, tell me if I'm missing something here. I'm sure that I am. There are two black holes that are colliding somewhere out there in space. Yes, and the impact of that is that somewhere here on the Earth, there's lasers that are a mile apart that can measure the impact of those ripples.
Yeah, you can think of it as like an earthquake out in the middle of the cosmos. And what we're measuring is the waves through space, the actual fabric of space.
That's really cool.
I love science.
Yeah, that's freaking cool. Like, how do we know that? I'm guessing it's an hypothesis to think that that these wavelengths are coming from a black hole, or do we know from some other source of data that there's a black hole or two black holes that are about, you know, X distance away, and so we would be feeling those impacts about now, or is that all just we kind of think that might be the case?
Okay, now I'm going to get myself too far out over my skis, but essentially, if we have a couple of these. So if you measure the same wave at different points of the Earth, you can try to triangulate back a general location.
Okay.
And so now you know, roughly speaking, where it happened, and you can try to look for that causative body. But at the same time, that body has moved in the amount of time it took for those waves to come here.
So if
you make an assumption, or you can guess how far away it happened, then based on the amplitude, you can guess how much mass is involved. But when you do that, the only things that make sense are black hole mergers.
Okay.
Because the masses required to create this, under our understanding of physics, is just so astronomical. That's the only option left, right?
That's wild that we have that, even just so you can have that much understanding of something that like a black hole. That's, you know, for me, for a non-scientist, that effectively, I mean, I know it's out there, but like, I don't know anything about it. And so like, it's so far outside of my realm of understanding that I just think that's amazing that we actually even have that much information on it. Thank you. Thanks for going there. The other question I was going to ask was around your modeling. And I was just curious how you're using AI in your modeling, how that's changing your work in your field, if at all.
It's definitely changing things. How rapidly is a little bit confusing. Industry-wide, I would say there's a lot of snake oil salesmen out there. Like, AI is going to solve your problem, get all this into your workflows, and it doesn't do anything. They just piss away money.
Yeah.
That said, there is some real world AI technologies that are starting to creep into things. So there's like mineral prospectivity, where you give it a bunch of different layers. So you might give it the gravity map. You might give it sections of a model in 2D. You might give it topography. You might give it XRF or remote sensing data, other layers and stuff like that. And then you say, okay, these areas over here are the areas where I know there's gold. And this is true. And these areas I've tested over here do not have gold. Now, using all the data, find me more gold. And so it's using AI to basically create a heat map of where there might be more, or where it's prospective for there to be more gold or whatever it is that you've trained the model to find. And so that is something that I would say generally, I think a lot of geologists and those in the field find underwhelming, because a lot of the times it shows them a map and they're like, well, I already know that area is prospective. Instead of looking at it and going, okay, so it's not showing me anything new. Therefore, I have explored or understand this. There's nothing I'm missing. It's still telling me something.
Sure.
And so there's a little bit of a reticence, I guess is the way to say it, in the industry to accept some of these things. But there's also other things that are moving along. And I can definitely talk about this. It's brand new out of my company. It's really cool. It's going to be probably way too technical, but nevertheless, I'm going to give it a go. Inversions are inherently non-unique. There's too many unknowns and very little knowns. That's why when I create a 3D model of magnetics or gravity, it's non-unique. That's why we're making assumptions and things end up being quite blurry. Where in real world, you have a fault plane and it's quite stark, the contrast in, let's say, density from one side of the fault plane to another. There's like a hard line sometimes in geology. But in an inversion, unless you've given it information, it's not. We also, throughout the process of finding minerals, the only way to ground truth whether or not you can build a mine there is to go put a hole in the ground.
Sure. Yeah.
And they're many hundreds of thousands of dollars, often $1 million a hole. So they're quite expensive and you want to de-risk them. You have to do that to raise more money to explore and eventually get it towards a mine. So you collect that data, you get the geology out, and that's your ground truth. What we're doing is we're using AI to connect or interpolate between boreholes and feed that information as constraints into the inversion. So we're creating a 3D model that, yes, it isn't perfect, is still going to be non-unique, but it is much closer to the geology because we're using the AI to create basically the geologic model of the Earth while we're inverting and keeping it grounded in the constraints that we have.
When you say inverting, does that mean that you're taking the data, like instead of building like a model based on hypothesis, you're taking actual data from the Earth and turning that into the model, or what?
Yep.
What are you? Okay.
It's a mathematical process, and then so it's a two-step process. You first compute, or the effect of usually is a half space, so just a single density for the whole Earth. What would that look like at all these different points on the Earth?
Okay.
And then it says, okay, I need to change my model, my starting model, to make the fit better to the real data. And so it changes it bit by bit, bit by bit, bit by bit. And they're to minimize the misfit between its synthetically produced data from the inversion and your field data that you collected.
Wow.
And so what we're doing here is help using AI to draw in lithologies and make that process much more integrated. So it's integrating the geology directly instead of having it always separate into two different silos. We're kind of combining the two. And so although AI is being used here, it's still really reliant on those expert knowledge that you have developed as part of putting together that geology, because the AI doesn't know the geology. It's just basically connecting lines in ways that you've kind of told it has to be for this particular area.
That's pretty interesting. So do you think that you said this is new stuff coming out of the company? Do you finding it to be somewhat effective, or is it more?
We're still kind of in the early days. We've had one full project, like production project, and it turned out amazing.
Really?
Then
you went and you back tested it, or you what did you use the word for gathering the data from the Earth?
Ground tested.
So, yeah.
No, not yet. So this is like just wrapped up.
Nice.
Hoping, I'm not sure what your publication schedule is, but probably by the time this goes live, that press release will be made and we'll be able to start to use that data because it's a client's data, right? And you can't fully talk about it until they've given you permission to do so because they own the data. And once they give you permission, then you can do things like publish it in peer-reviewed journals. You can use it for marketing and that kind of stuff. So I know it'll happen. I just don't know when.
Okay. I'm going to make a note to circle back with you on this is my note. I'm writing a date to make sure that we can use that part.
Oh, you can use what I just said.
Oh,
It's
okay,
just,
cool.
No, I didn't tell you the name of the company. I didn't tell you
Okay,
where the
good. Just
data was.
okay,
I just told you that we can do it, and we worked with a client.
got it. Okay, copy that.
It's perfectly fine.
Okay,
I didn't cross any lines.
Great. I'm just looking out. I just want to make sure. So I'm good deal. Can you say, is this like a homegrown?
Yeah, it's totally developed in-house from us. It's pretty awesome.
That's
I
cool.
didn't develop it. I can't take that credit. I can take some credit on the direction it's moving because I'm the closest thing that my company has to a geologist. So because I took so many geology courses as a part of becoming a volcanologist, I know a lot more geology than your average geophysicist. And so being able to take those drill logs and make sense of them and then make sure the brainiacs who created the code and know how to, because it's still in the stage that they're the only ones that know how to use it. You know, in the development timeline of something, at least in the fairly early going, it's like the handful of developers that know how to use it.
Yeah.
And then eventually they get the bugs out to get the workflow, and then it becomes a bit more easy for other people to pick it up. So we're moving into that phase of it. And I think it's actually going to be a game changer for the industry.
That's cool. Have you ever been to one of the sites where they actually are drilling cores out?
Oh yeah.
Are those machines just like? I would always imagine that they would be pretty impressive. I mean, to just cut holes into the earth.
It depends on what you mean by impressive.
I don't know. Like, how deep are they going? I should say.
It depends. It can go. The ones I've been with are 500 meters or so is kind of the limit. But the ones that are more impressive are like for oil or geothermal, and I haven't been on those because the core that I'm dealing with is about like maybe this big, right? That's kind of the core that you get for the Earth. Maybe probably a little smaller than that. But for like hydrothermal and stuff, you're like it's a proper size thing, and they go quite a bit deeper, and they are really, really expensive. And that's why geothermal is so hard to really finance and get going, because there's so much risk if you miss with your drill hole and where the reservoir of hot water is not as permeable as you thought it was or something. There goes $3 million.
But I mean, even to be able to drill 500 meters into the earth, that's pretty cool, you know?
The Russians during the Soviet era still had the record for the deepest drill hole ever drilled.
What is that?
I can't remember the exact depth, but it's over, I think it's over 10 kilometers. I think it's like 14 kilometers deep.
Whoa.
It's some crazy, crazy number. Yeah. And it was the Soviets that did it.
Did they share that? Do we have data from that? Like what?
I know there's data from it, but it's right in the middle of the craton. So, I mean, there is data. I know it's published. I've never dealt with it.
That would be fascinating. I mean, you said 14 kilometers. I obviously I'm not going to hold you to it, but
you can't hold me to that number, but it's still the record.
It's freaking lot. It's a long time.
It's a lot. It's by far the deepest we've drilled.
I mean, even if you were going to say like it's over, 1 kilometer deep, like I'm just thinking of that. That's amazing. That's pretty cool. I'm going to look into that.
Yeah,
that's cool. Okay. So you said, as you got into this new job that you still kind of had an itch that you needed to scratch. You decided I'm going to start a podcast, and like curious how you came about that decision, because I mean, there are a handful of ways that you could have scratched that itch, so to speak. Right.
If I'm actually going to tell how I got into that, it has to actually start during the postdoc when everything comes full circle. Right.
Yeah.
And so when I was in that in-between stage, trying to hustle, find a job and find meaningful employment, we actually came up with the idea of selling academic knowledge to TV North or Hollywood North here in Vancouver, British Columbia.
Okay.
And I had a Rolodex of a whole bunch of different people from different, chemists to healthcare. I knew a lot of people from a lot of different disciplines, and we called it Eggheads Consulting. And I started talking to other creatives in that space, and it was just kind of a really neat idea. I even had an agent at one time try to steal the idea out from underneath me and just say, give me all your contacts and I'll run it. And I was like, wait, what? Yeah. And then the pandemic happened and that fell through and everything else. But it was just like an introduction to a different way of thinking and communicating that I wasn't used to before that. And the other part of it was, at around the same time, I had an interview in actually Wichita Falls, Texas for an academic position. And I had to come up with a research portfolio. And I came up with this really cool scientific story. And I'll get to it in a second. And that was really the real impetus to I really want to tell this story. But as I started to do it, I actually wrote scripts, I recorded some stuff, and then I realized it's only going to be like 8 episodes long. Unless I get this picked up by a network, no one's ever going to hear it. Like, it's, if you're going to build it, they will come. You have to be consistent. You have to put the time in. You have to build the audience. And 8 episodes isn't just going to do it. And so it hung on a hook for a couple of years until I got this job. And then I was like, you know what? I should really revisit this. I still want to tell that story. But fundamentally, I also have this passion for science writ large. And so being able to talk and communicate about science is really something I want to do. And I don't care if I make money out of it because I've got a good paying job. I can do this on the side every couple of weeks. As long as I can set a schedule, I can stick to it. So that's kind of how that came together.
That's cool. But there was a side story. I think we skipped over part of it. You said, yeah. Go ahead.
So in Wichita Falls, one of the things I needed to do was to come up with like, okay, if you get hired here, what are you going to study? How are you going to make this university better? What kind of things are you going to get yourself into? And I was like, okay, rural Texas, there's no volcanoes. But New Mexico isn't that far away. It's only an 8-hour drive to the Rio Grande Rift. And this is an area where North America is actually pulling itself apart. You have one part of North America rotating away from the other part.
Really?
They're kind of unzippering. Yeah.
That's cool. I didn't know that.
Yeah, it's...
I know it's a long time, but it's still also kind of terrifying. If you think about it. I know it's probably going to take like thousands or millions of years, but still.
Well, it has a volcanic eruption about every 6,000 years or so. Is kind of like the average, I think. Again, don't quote me on that for sure, but it's in the thousands of years. I think it's at least 5,000 years.
Okay.
They're also the home to, I think, the largest known magma body in the U.S. I'm going to butcher pronunciations, and I apologize in advance. The Sakaro magma body, it sits pretty close to underneath the town of Sakaro. It's actually off to the side. It's not directly underneath the town in New Mexico. And it's quite a large, it's inflating, so you can see the deformation at the Earth's surface. So back to geodesy and looking at the deformation of the Earth. But what really brought me to that area was actually an eruption near the town of Carrizozo. And I can't pronounce the actual name of the flow. I think it's Las Maples. I'm just going to call it the Carrizozo lava flow. It is the longest lava flow in the continental U.S. It's 75 kilometers long. It's huge. So if you want to compare to Kilauea, so the Pu'u'o'o eruption basically erupted from, 1986? Oh, I hate being put on the spot. It was like 36 or 38 years that it was erupting from Pu'u'o'o and the area around it. During that 30 some odd years, it erupted 3.3 cubic kilometers of material. That's a lot of material.
That is a lot, but also I was just thinking, comparing that one you mentioned a while ago, Mauna Loa with 100 cubic kilometers.
And that was really a debris flow that just goes like that. Like, it's crazy.
Why?
So
wild.
The Carrizozo flow, though, was 4 cubic kilometers. Wow. And that is huge. It's a massive amount of material to erupt. The current understanding, or the current, we'll say, peer-reviewed research kind of proposes that this eruption happened over 30 years, in the decadal kind of scale. The problem with that is that, well, first off, when you look at volcanoes that can stay active for decades, where are they located on the Earth? It's places like Hawaii. It's like places where you have a direct mantle to Earth's surface kind of conduit. And you can think of this at like Stromboli is a good example. Urta Ale in the East African Rift. You can go, like, there's a number of volcanoes that can actually have persistent long-term eruptions. How do you have a constant long-term eruption if you only erupt every 5,000 years or so in this area? And it's not even from the same volcano. It's just a broad area. So it doesn't make sense. And if you look at the pressures and everything else, although I haven't done the math yet, it also doesn't make sense. So that suggests that this eruption happened relatively fast, probably in the course of maybe a year. So 4 cubic kilometers material is a crazy, crazy number to come out in 1 year. So have you ever been to an active volcano, just out of curiosity?
No, I never have. I'd love to. I just never have.
Have you ever been downwind of a industrial stack or something like that?
Yeah, for sure. For sure.
Yeah, it's not pleasant, right?
It smells terrible. And like, I mean, I used to spend some time in it it doesn't matter. But yeah, I know exactly what you're talking about. Any of them, like a paper mill smells terrible. or any
Volcanoes
of those
do the
things.
same thing, right? They pollute.
Yeah, of course, makes sense.
They send off a lot of hydrogen sulfide into the air. In fact, Hawaii deals with acid rain all the time, right? And so you're putting all these volatiles into the air. And that's the real danger. So the only thing we have that's even close to comparable, and it's not really comparable because it's so much bigger, is actually an Icelandic eruption in Iceland in 1773. It's called the Laki eruption. Oh my goodness. So it's 18 cubic kilometers of material. Like, it's just astronomical. In the course of
that is insane.
18 months. 18 months, it pumped out this amount of material. It is insane. And here's the crazy thing, is that 80% or 80 to 90% of all livestock on Iceland died. Fluoride poisoning. So you have hydrogen fluoride that comes out in these volcanoes, and it's usually such a small concentration. But when you're pumping out 18 cubic kilometers of material in 18 months, and then it gets deposited onto the grasses, they end up with fluoride poisoning and dying. Famine caused 20% of Iceland's population to die. Then you had this volcanic fog, so volcanic pollution, waft over into Europe. And the British, they built an empire through bureaucracy. And even at that time, they had really good death rates, like being able to tell who died and when. And so we have an excess deaths in that summer that this volcanic pollution, because at that time, people weren't running computers. They were working the fields. That's how people made money.
Yeah.
And so they're out in the fields, they're in this pollution, and some of them succumb to health problems of that. And so you have all this excess deaths of tens of thousands across Europe at the time. Now, given Carrizozo is smaller, it's, a third of the size, a little less than a third, but you still can't ignore the amount of volatiles and caustic gases that are going to come out over the course of about a year with that much material. And that's really the danger. And it's completely, I would say, in the rock record, because we can't date things on the year-to-year basis.
Mm-hmm.
If this happens at another volcano, we'll never know.
Just why wouldn't we know if it ever happens in another?
Well, because we don't have the ability to say, this whole lava flow was erupted in 1 year.
Oh, I see what you're saying. If it has happened, not if it ever happened again. Sorry, I misheard that.
No, yeah, if we're around to observe it, then we can see it.
Okay,
but the thing is we don't know how prevalent this type of eruption with these high volumes and lots of gas. I mean, we know that they've happened in science. We talk about the Deccan traps as one of those possibilities for an ancient extinction event. So we do know and understand and have for a very long time, since... Yeah, we started this conversation that it's modern geology starts at around the late 1950s into the 60s. So long time in a modern sense.
Sure.
So we know that they have this capability, but we haven't really we can't easily recognize it from the rock record. So we don't really know how often something like this happens. But the hazards associated with it are mind-numbing, because it's not the lava flow. Yeah, the lava flow is scary.
Sure.
But you can get out of the way of that.
Well, I don't know if this is the same, but wasn't there a pretty big eruption in Iceland, like around, I don't want to call it between, 2008 to 2012-ish. I remember that there was a big eruption over there, enough that they were diverting a bunch of flights around the area.
You're talking about the volcano that I can't pronounce.
Okay.
Something. I'm sorry.
Let's call it the big volcano that was around that time. Do you have any idea off the top how big that eruption was? I just remember it was impactful enough that, like I said,
So it wasn't that big of an eruption. The big thing is that you had a bunch of this lava ice interaction. And so when you get a lot of hot rock and you can get a lot of water into it, you can get a lot of steam and you can build up a lot of pressure and you can get these large explosions. And it's not an explosion in the sense of like Mount St. Helens. It's like enough magma came in contact with the water and the ice, the groundwater, caused an eruption, put all this ash into the air, but it's only got to go to Europe, right? It's not going to North America or all around the globe. So it doesn't have to be that large to come over the UK and go, maybe we shouldn't fly in it. Because what happens is that glass gets into a jet engine, reheats and then melts and then reattaches itself to the engine. And so you gunk up the engine and
That's a good point.
It's not good. And so that's the reason why all the planes got grounded, is because you don't want that ash into the engine.
Makes
because
sense.
it's quite scary.
I'm looking for a data point at all that can help me realize how similar size and scale. So like then you mentioned Mount St. Helens. That's obviously a big one. Do you have any idea of like what I don't know what one was?
So we deal with those type of eruptions a little differently. We put them on a volcanic explosivity index, and I
Okay.
think that would have been a 5. Basically, Mount St. Helens was about 1 cubic kilometer of material was explosively expelled from the volcano.
So 4 times as much as the one because you said the other one was 4.4, the one in New Mexico.
Yeah, so there's 4 times more material being erupted, but it's a little different. Like Mount St. Helens also, like if you added up all the dome building eruptions as well that has happened afterwards, like that's not included in the explosive ones. So, but yeah, the hazards from an exploding volcano, like a big eruption like that, are quite different than from an effusive one, right? But again, size matters when it comes to volcanoes.
Thanks for separating those two, because in my mind, all volcanoes are blowing up like Mount St. Helens.
No,
But okay.
most of them don't. Most of them are like Hawaii in some respects. I mean, yes, there's usually some explosive component, but it's not like Mount St. Helens. Those don't happen very often. In fact, we've kind of had not that many of those type of eruptions in the last while. They happen.
Sure.
But
Obviously.
I mean, the biggest one in like living memory is Pinatubo. And that was in 1991, I think, or is it 94?
I couldn't tell you either way.
Either way. So it was in the 90s and it erupted somewhere around 10 cubic kilometers of material. And it was like the first real good data set to kind of predict climate change, actually, because then all the sulfur aerosols that get pushed into the upper atmosphere actually reflect sunlight.
Mm-hmm.
And so usually those big, large volcanic eruptions cause a cooling of the earth. And Pinatubo did as well. But we recovered much faster than the climate models at the time suggested we should, based on the amount of sulfur that was put in the atmosphere. And so it was like another data point to show that climate change is going to suck.
Sure. So it's like we have a model. We think, oh, we're going to recover in X amount of time. It turns out that got shrunk. And so we have to realize, okay, there's something else going on. And then that helps us understand. That's really interesting. The spillover effect from those kinds of things in the science world is really, really
That's why I love science. That's why it drives me crazy when people say, well, why'd we fund that? And you're like, because you don't know where it's going to lead. You don't know where it's going to spill off. I mean, yeah, it might seem silly, but you don't know is the thing, right? Like you just have no idea. And so you have to make a decision based on the values of society of like, what do you want to do? It's the same idea of spending money on arts and culture, right?
Sure.
It's like, what is your value? And you don't know where this is going. Are you willing to take a chance? And I think with all of its faults and foibles, keeping in mind I'm Canadian, that is something that the US has actually done really well in historical sense since, the Second World War, or even before that. Like they really put money into science and technology, which is what has created the country that it is today, is because of that. They made that conscious valued decision. And it's sometimes I struggle with the fact that I see too many people trying to go backwards on that when that's how they got to where they are today.
I think that's a great perspective on well said. Thanks. I love it. No notes, nothing to add. Well, so let me ask you this. So where do you want to take this from here? Yeah.
I don't know. It's something that I enjoy. I enjoy the podcast Whimsical Wavelengths because I learn so much more. Being able to communicate. I was also like in high school in the debate team and stuff. I never made any friends there because it was just the cultures didn't jive. But I like the ability to like communicate and argue and be persuasive.
Mm-hmm.
At the same time, I'm really passionate about knowledge and making sure that people understand it. And so we don't end up going and retreading on or throwing away things that are really important to who we are now. And there's lots of good examples about this that give a weird one that I don't understand why it is a problem would be vaccines. Like, why are we going backwards on these when the data is pretty clear? That's not to say there isn't nuance, there isn't messy things. Like anything in science, when you get down to the details, there is some mess. There is always mess. And there's mess in looking at vaccines on an individual basis because maybe you are immune compromised. Like there's reasons that maybe you don't want to do something, but on a population scale, it's like, I'll roll up my sleeve anytime. Like, let's go. I mean, obviously there needs to be a scientific reason for it.
Sure.
But the way we've developed our public health is all science-based. And again, mileage can change on an individual basis sometimes because it is, every person is unique and their circumstances can be unique, but on a population scale, I don't understand it. And so being able to communicate science is a way to be able to build that bridge to being able to understand the scientific method, to being able to make sure that maybe this happens less. And so not only do I get something out of being a podcaster because I learn so much more, it makes me a much more knowledgeable person. And I get to see how the world is changing in ways that perhaps other people can't. But then I get to communicate that and share it. And so that is very rewarding to me. And that's why I'm going to continue doing the podcast. But I also feel like I might be eventually being able to make a difference.
I mean, I think I really like the way that you explain that. Tell me if I'm making too far of a jump here, but I was thinking while you're explaining that a little bit about how, you started down your professional journey or at some point you made the decision that you were going to try to stay in academia as a teacher. And now you're a teacher. You're not teaching formally in a classroom, but your lectures on a podcast, you do a really good job at teaching what I think to me are somewhat complex ideas in a really, really good way. You boil them down, you make them understandable, and it's got a good cadence and structure. I really like it. So, I mean, is there anything to that? Like, do you see it in some way as you're an educator?
For sure. I mean, there is part of that for sure. And like being able to teach or educate also forces you to understand the material better. Like there is that aspect to it. So if you enjoy teaching, you're almost, generally speaking, enjoy learning, right?
True. I think so. Yeah.
At least the good ones anyway. I mean, some people just,
And
we've all had them.
But in that, to your point, like if you're the good teachers are I feel like the people who I learn from that I really enjoy learning from are the ones who enjoy it. And they're not, they're probably just ended up in a job they don't like. But I think that's neat, man. I think you're doing, what are you excited about that's coming down the pipe? Do you have any topics that you're working on that are coming down that you're
to be fair, a lot of times I'm just barely like I keep a little bit ahead, but not so far ahead that I'm like, oh yeah, I can point to this thing down the way. But in reality, I'm going to point back to Carrizozo because we are going to do this at some point. So I'm still good friends with my past PhD supervisor. I actually had him on the podcast not that long ago. And I tried to make him make fun of me and I couldn't manage to do it. It was all about a Canadian volcano called Mount Meager, Canada's most dangerous volcano. And not because it could erupt, but because it could fall down and create landslides. Anyway.
That's an ironic name for a falling down volcano to call it Mount Meager too. I feel like, like it's a meager volcano. It's very meager in size.
Yeah. And so the whole Carrizozo thing, I've convinced him it's a worthwhile science project to get students on, and we will do that eventually. Unfortunately, us being outside the country, not within the United States of America, going down to New Mexico, we'll have to wait until such time as we feel comfortable sending international students there, essentially. I don't know how else to politely put it, but it's not worth the risk. But it was covered in the most recent grant that he got through the Discovery Grant. And so there was an earmark for it, but it's going to have to be delayed until such time as we can make the logistics work.
Makes sense. Yeah, I totally understand. There are a lot of complexities at play there. I'll read between the lines on that one. What's your favorite episode so far?
So far, I would say it's the pair of them. I almost want to redo it because it's just one of those things you do it and then you're like, man, could I have done that better? And I'm pretty sure you've listened to one of them, and that was on Dr. Claire Patterson and finding the age of the earth and finding that industry had polluted the world with lead. But the first episode before that one was actually with Thomas Midgley, the engineer turned chemist that actually created the lead problem. And he also created the CFC problem, which required the Montreal Protocol, I think in 1984, because CFCs were destroying the ozone. And so that's why aerosol cans and stuff were banned for a while.
He invented the CFC?
Yeah, he did that as well. And he also invented his own death. It's a little glib to say this, but he ended up with polio. And
wow.
so he became essentially paralyzed. And so he invented a series of pulleys and stuff so he could still do stuff from bed. And eventually he was found tangled up in it and
Oh,
essentially
wow.
hung.
That's terrible.
It's terrible. And it's funny because he invented these things. And now with retrospect, we see him as like this evil guy in some respects because he, invented these things that almost destroyed the earth twice. I mean, you could easily make that argument. However, he was only solving a scientific problem at the time.
Yeah.
And you can still say he was a bit Machiavellian in the sense that he was willing to ignore the data that showed that it was bad for you. And there's a couple instances in the historical record that show that. But at the same time, is like, was he? Like, is it more of a failure of the system? Because it was only after we started to get government apparatuses, and this isn't just in the US, this also happened in Japan and other places. It just, industry where it is, it centers on the US, a lot of this stuff. And it was the EPA, environmental protection agencies, and these sorts of things that happened in the 60s and 70s that got put in place that really allowed for the data to be collected to show that this is a problem. The science could be done only because of government. Otherwise, we spent from like the late 20s until like the 60s doing nothing about it.
So you explained it really well. So what's missing from the episode that you want to redo now?
It's just, there's certain themes that I don't know, like you can always be your own worst critic, right?
Yeah, that's true. Yeah, I get that.
And so it's try to talk when I do these solo episodes, and the vast majority of my episodes are actually interviews with scientists who I take one of their papers and then try to boil it down and make it make sense to the average science curious person. But when I take these solo episodes, generally speaking, I'm trying to take more of a historical arc and show that science is messy. It is a human endeavor. And it's not just messy on the scientific end, it's messy on the people end. Like there are people that went out, like the guy who went out and tried to prove Aristotle was wrong because he just hated Aristotle, and then proved
He's got
that
a grudge against Aristotle.
Absolutely. And it's just like, okay, that was his reason for doing it, but he proved that sound and light traveled at different speeds.
Yeah.
And he did this just to prove Aristotle wrong. And it's mind-numbing, but at the same time, it's such a human thing. Making science, like, how did we get to the present? Like, understanding that, understanding the scientific method, and understanding the messiness of the people involved, because we as scientists too often try to extract the human from the data.
Mm-hmm.
And it makes sense to do that in an academic literature because the data is what matters. It's peer reviewed. But when you're trying to tell a story about how we got to where we are today, if you remove the person, it doesn't connect to people.
Yeah. And it's also
and so
like,
sometimes I wonder if I'm not reached the level of storytelling ability that I want to.
well, that's
it's always going to be a work in progress, and that's fine.
Yeah, I mean, isn't that part of the, I shouldn't say isn't, but let me rephrase that question. I mean, is that part of what makes it, isn't that like part of the joy, right? I mean, that it's still a little bit messy,
Absolutely.
like it's a work in progress. If you'd already nailed it, as good as it can be, like it would be boring. At least I think it would be.
For sure. I got to say, the solo episodes are a heck of a lot more work than the interview ones. Holy smokes.
I can only imagine. I haven't ever attempted one like that, but I mean, it takes a decent amount of work to just prepare for an interview, as you know, but like also if you were going to create a whole script, and your stuff's really well done, it's polished, you clearly have facts, sources, all of it. And so I can imagine that would take a lot.
Yeah. And even if you do use AI, you got to be like, okay, did you hallucinate? And you got to go track down everything. You have to make sure, like, what's the point of doing science communication if you're not going to cite your sources, or at the very least, go to the source material?
It's just going to be a quick way to get embarrassed. If not, like I interviewed a guy a little while ago, and he was telling me about how he's an attorney, and he was telling me how there was an associate,
the AI lawyers.
Yeah, there was an associate who had created something and put it before the court and some state court, and then it was citing case law that didn't exist.
I read about this. It's wild.
Yeah, it happens. So
didn't they lose? They got reprimanded for it.
I don't know exactly. I'm sure they did because they found out about it, and so I don't know what the impact of it was, but I was just like, ouch, that's That's not where you want to. That's not where you
No.
want to be.
No, not at all.
And what's been something really surprising that you've learned as you've started this thing?
I would say every single episode has something surprising when I do an
Really?
interview. Oh yeah. Because I mean, one of the coolest ones that I can think of off the top of my head was sounds boring, and then you dig into it. Like Dr. Hollister in the American Museum of Natural History, what he does is he's an entomologist, and he CT scans a whole bunch of insects to look at their breathing apparatus because they don't have lungs like you or I. They
Mhm.
have these little tubes, and sometimes they have little air sacs inside that do this, that pump air in and out. But generally speaking, it's just passive airflow through these tubes that allow insects to breathe. And just that conversation about, like, okay, back in the Earth's ancient history, we know that insects got very, very large, but they didn't get the size of dinosaurs or anything. So was it this breathing apparatus as part of the reason that they couldn't manage to get any bigger? Was there like an evolutionary, like having
That's
those types
wild.
of discussions are just wild to think of, but yet to have them with an expert who has, started to look at the evolution of insects writ large and the breathing and having this like discussion is really cool, especially at a high level. Like we're not just sitting there spitballing, throwing darts at a board. No, this is like based on what we actually understand, like surrounded by data. And I'm often blown away by it.
That's cool. I didn't know any insects were bigger
Yeah, there
in the
was a
times past. I
particular
didn't know
time
that.
frame that they were quite large. We're talking, beetles like, a couple feet across type thing. Dragonflies like quite
That's
large.
wild, dude. That's wild. But we know they were there, but we don't know why.
We don't know why they didn't take off. Like, why did they not proliferate, stay that big,
Yeah. Why they
outcompete
get
things?
smaller? Yeah.
And then they became smaller to outcompete. So like these sorts of things are, I mean, we have some idea, like it's not like we're completely data void, but it's a discussion nevertheless, right? It's a hypothesis that we can't directly test because that happened. I can't even remember. Was it 300 million years ago?
Sure. Let's give or take,
Yeah. I mean, it's a long time ago, well before the dinosaurs.
Dude, that's crazy. As it seems like we're always learning new stuff, right? I mean, is there anything in the scientific world that right now you see as like this is a widely regarded, accepted as fact or truth or the closest thing to it that's going to be that you think will be overturned in the near future? Or
See, that's tough because we don't really know. I mean, I've already mentioned the idea of gravity and quantum mechanics
yeah.
and cosmology, and that's kind of the big domino that has to fall at some point
Mhm.
if we're going to get towards kind of a unified theory. But is that going to fall in my lifetime, 1,000 years from now? Is it ever going to be able to be solved? I don't know. Like we're not necessarily that close. They are starting to build a new so CERN is the big particle
Mhm.
accelerator, and they're planning a bigger one as like the sibling or the next better thing for it. I know China was as well, but they put that on the back burner for some reason, something to do with politics that I don't understand. So I think the next one of those for particle physics is going to be CERN. There's new stuff for space coming out all the time. The Artemis missions are going to be quite interesting. I know they changed them recently. I'm
Yeah, I
not
heard they got delayed,
exact.
and I don't know when they're gonna. I don't know.
Well, they got delayed because of something specific due to a fuel leak, but I think they've solved that and it'll launch soon. But it's more Artemis 3 was going to be the next moon landing, but now
Mm.
Artemis 3 is not going to be, and Artemis 4 is. I'm just not really sure what the ramifications are of that at this time. But the ability to go back to the moon and actually build a moon base, having to bend and get resources from the moon and finding new ways to solve that problem is going to really push the boundaries of what we can achieve engineering wise and science wise. So that's going to be really cool. I actually had somebody on from the permanently shadowed, oh my gosh, PSRs, permanently shadowed regions of the moon. Somebody with NASA came on not too long ago, a couple episodes ago.
Oh, that's
And
cool.
basically these areas that are shadowed, they potentially store volatiles that are necessary for life. Like they could have water. And so that's a resource that if you built a moon base, you could tap into. And we're getting really good at recycling water on the space station and stuff like that. So once you have some water, now you can put those systems into place and you don't have to truck it all the time from Earth.
Yeah.
So
That's
like
fascinating.
that's a straight on practical thing that's coming
Yeah.
out of the science if we want to explore the solar system and potentially the galaxy.
I mean, to your point, like they at a small level, they're really good at it on the space station. And we've also seen that be replicated out in larger scale here on the Earth. You know, like I saw an interview. This has been several years ago where I saw the city manager of Las Vegas talk about their residential water recycling and how effective it is. So I mean, it's another desert. It's obviously a different desert, but it's a big scale. And so I guess if you can scale a problem, then you can scale it here. You can theoretically scale it somewhere else. That's
Yeah,
really,
sure.
really interesting. I love that. Yeah, that's cool. Is there anything that, you know, that you're aware of that people are working on that you're just really excited about? Like potential research that's going on that you're just fired up either in your field or otherwise?
Okay. I guess. I mean, there's always stuff. That's the problem. It's like, what do you pick? But I guess something did fall into my LinkedIn feed. Somebody was like, I published this paper on Hawaii. And I was like, oh my gosh. I read the paper, at least I didn't read it all the way through, but I read enough of it to go, I know exactly what this is. This is amazing. How do I say this without getting too far into the weeds? So when we talk about,
Just go into the weeds.
well,
Let's get all the way in.
Gotta be a little bit logical.
Okay.
So let's just go back to Carrizozo. I've already explained Carrizozo. It's 4 cubic kilometers material. But if you don't have a whole bunch of stuff coming up from the bottom to support a constant flow out, that means as you erupt, you're depressurizing other batches of magma down below because you're removing pressure. You're removing pressure from the system, which can destabilize those. So you've got to think of magma a bit like your soda bottle. It has all that gas. We've already talked about all this gas is in magma. That's actually the reason why volcanoes erupt is because of the gas. Otherwise, the magma would be too dense. So if you all of a sudden reduce the pressure on this magma because you've erupted one, now gases come out that destabilizes that one and erupts that one sometimes.
Okay.
And we see this in Iceland pretty clearly, and we have seen it in other places where that's called like a top-down effect. As you remove pressure or unload pressure, you erupt more and more and more. What the paper, if I'm understanding it correctly at this point, is making the argument is Hawaii, it's the reverse. It's not top processes that are affecting deeper reservoirs. It's that the pressure control is all from deep within the volcano, essentially from the mantle. So that what that means is like it has an effect on how you would view the processes leading up to an eruption in Hawaii.
Okay.
For instance, and how an eruption is going to continue in Hawaii versus an eruption that is going to happen somewhere else where it's more top down. Because what you'll see in a top down system, particularly if it's a big silicic system like Mount St. Helens or something, is you get a cascading effect, one to the next, to the next, to the next. And then once you've erupted all that material, it ends.
Okay.
That's just it. It's top down control. Whereas if it's bottom up control, it's just whatever's happening down here where you can't see it. That's controlling the outflow.
Interesting.
Now, there is some caveats. There is still an upper level magmatic system that does modify the effect, but the argument is, I'm pretty sure I have to reread the paper again. I might be quoting it wrong, but it's the dominant process is coming from deeper. And that's really interesting and can it's not like a game changer. It's not like a complete paradigm shift, but it is a different way of thinking about the problem for that specific volcano. And maybe that's a good segue to say every volcano is different. Everyone, you could say, has a bit of its own personality. And if I were to throw in a bad science joke, I don't have a favorite volcano because they all have their faults.
That's a good, I like that a lot. That's solid. Look, this has been awesome. I really enjoyed this. I'm going to pause the form of podcast for a second and just say, before we move on, is there anything that you want to cover that we didn't cover? Anything you had in mind that we should jump into? Or do you feel like this is a decent place to move it on, wrap it up?
Yeah, I mean, it is a great place to move it on. The only thing I'll say is that the podcast has been really good fun. I thoroughly enjoy doing, as all this said, and I'm still learning, but I also won an award recently for it.
Dude, huge congrats. I saw that. That's amazing. So tell me about that process of how it worked out with your award. That's really,
it's one of those funny things is like when you have a niche film, for instance, you're going to go put it into a local film festival. You're not going to go shoot for the Oscars right away, right?
Yeah,
And so
likely.
that's the analogy that I'm going to use.
Okay.
And so the American Writing Awards usually does books and stuff like that. They obviously care about writing and I guess scripts more than some of the other podcast awards that would be out there.
Sure.
And they've been around for a couple of years doing a podcast award. And I looked into whether or not they were real, because the way you give them money for it is through PayPal, which is a little weird. It worked out fine, obviously, but it's still
Nobody
a little
stole
bit of
your
a
identity yet.
I wasn't expecting that, but it's just kind of like, how legit is this if PayPal is the means that which you
It's funny.
could do it? But I mean, I shouldn't really complain. I have a geophysical society here that I belong to that also gets money through PayPal as well.
Hey,
But it's usually volunteer type stuff. It's a small organization, perhaps. Anyway, I looked into who were past winners for the science category, and I figured that what I am producing is much more directly classical science. I felt like I was at least competitive on an audio basis. If I am an army of one, I don't have a sound audio engineer, I don't have a producer, I don't have anything. It's just me doing all of it. So I figured I was at least competitive, if obviously potentially not better. But I figured my topics were much more science, and I figured, why not? They seem legit. They do really interesting things in the book sphere side of things, but they're relatively unheard of on the podcast side. And what do you know? I won. It's like, again, you have to be willing to put yourself out there. You
100%.
have to be willing to, occasionally swing for the fences. And this time it worked out.
That's awesome, man. I think that's, and you know what? It's got to be kind of validating, right? To hear from,
For sure.
yeah, I think that's well said. And for what it's worth, everything I've seen, I think it's completely, I think it was a well-made decision on their part. I mean, I think your podcast is really great. It's super informational and entertaining. Like, I really, for anybody out there listening, I think you really enjoy it. I'm clear. Anyone who's also listened this far, that I'm not a freaking scientist, and I really enjoyed the stuff. So you did a great job boiling it down, keeping enough context, information to help a donk like me be able to understand it. And so anyway, it was just, it's a great show. I highly recommend it for everyone. Whimsical Wavelengths. And it's really well done. I like did you do your music at the beginning? Is that?
Yeah, actually, it's a story in and of its own right, actually, because at the beginning I was like, I need something. I want to brand it. I was like, okay, let's go to some AI music generator. It generated me some horrible lyrics, but it was close enough. I was like, I can work with this. So I spent, I don't know, hours editing them until I got something. I was like, okay, this works.
Hey.
And then put it in, it generated this music. I was like, that is way better than I thought it was going to be. I thought it was going to be crap. But then when I went to my second season, I was like, it's time to spend the money. So I went on Fiverr, got a real person to redo the music in the same general theme, same general way. And they added their own flourish to it, and it sounds great. I'm so glad I went with a real person who's doing the AI. It just sounds so much better. But it's what got me started, because that costs money, right? And when you're first starting, you don't want to, even if you're totally okay with the costs, even if that's okay, you don't want to sink that much in at the beginning, because you don't even know if you can do it, right?
Yeah. There's so many of those small decisions that you have to do. You're like, I just need something to get me going, and you get a little momentum, then you're okay. Speaking of that, how is your the last episode I heard you were talking about selling your first t-shirts? Can people get some t-shirts and some merch if they're interested in tracking you down?
Oh boy, that was one of the old episodes.
Yeah, it was. I heard it was just, you were just talking about it.
Yeah. So what that was a contest. I had made one. It had Jurassic Park kind of on it. I don't think I'd be allowed to sell those. So I was trying to give one away as one of the ways to get people to listen to it. I am trying to set up a merch type thing on Fourth Wall. Technically, it is live. Technically, there is a t-shirt there. I don't have it linked to my website at the moment, only because I have not yet settled on what I really want it to be, and then ordered it myself to be sure that I'm okay with other people having my name on it, right? Like, you kind of have to be, I don't know, maybe I'm old school.
Once. No.
Maybe I'm just old school. I don't know. I can't.
I get it. Yeah, I mean, because you can test, it's the same way you test and validate your own research before you put an episode out. You're going to make sure it works, and you're going to make sure that, you want to get one of those things, order it yourself, check it out, make sure it's, reasonable quality and people can get what they expect. It looks like you think it's going to look, and all that. I totally get it.
And arguably, it's not the money that I'm doing this for, right? I've got a fantastic job. I love my day job. I love my career. So I'm doing this because of me. And so adding on a layer for a shop and a layer for this has to be done slowly. Otherwise, I can't put out the podcast. And because monetization is just not at the forefront of what I really care about, eventually one day I'd like to break even. But huh?
No, go ahead. Keep going. Yeah,
it just is what it is. Like one day I would like to break even, and I feel like one day I'll get there. But that's not really why I'm doing this, right? Like it's not. It just doesn't affect.
Yeah, I totally get it. I mean, the value that you get from it right now it's coming from other places, and so you don't need it to. And I totally respect that. And I think that's like that shows up in the authenticity behind your show, and it shows up in the way people enjoy it, and clearly be in the way even critics are seeing it with the award that you're getting. So I'm stoked for it, man. I really enjoyed the ones I've listened to so far, and I'll enjoy the rest of them. I know. So anyway, really appreciate you coming on here. Jeffrey, either way, 6 Fs today. I've really enjoyed this, man. Thanks for coming on. I super appreciate it.
Perfect. And thanks for the chance. I am always up for talking about science.